welcome to the next head of emulsion polymerization. In this segment, we will discuss about the particle size distribution theory under the edges of emulsion polymerization. Then we will discuss about the implementation of the process in emulsion polymerization process. Now, before we start, let's have a look about that what we discussed previously. We discussed the particle nucleation concept, in which we discussed about the growth of polymer particles in under the edges of emulsion polymerization. We discussed the various factors involved in the particle morphology under the edges of emulsion polymerization. During the course of study, we discussed about the various reactors being involved in the emulsion polymerization process and their performance of various reactors under the head of emulsion polymerization. Now, in this particular lecture, we will discuss about the concept of population balance to be implemented in emulsion polymerization process and implementation of all those things into the emulsion polymerization process. Now, if you see that the particle size distribution, this particular aspect we have covered previously. Now, this particle size distribution is defined in terms of number density of polymer particles of unswollen volume, which is represented as small v, that is represented as NV. Now, as you recall that we discussed about the efficacy of the particle size distribution, because usually the polymerization process is tutored by various kind of polymer chain, and the size and numbers of those monomers, they also depend on the various factors. And whenever the size of those polymer chain increases or decreases, then it affects the molecular weight distribution. And we all know that the molecular weight distribution plays a very vital role in deciding the properties of polymer. So, that is why the particle size distribution is very much important in calculating the different properties of various polymers being generated or produced in course of emulsion polymerization. So, the units of NV are number of particles per unit of unswollen volume of particles. So, let us have a look about the mathematical approach of this population balance. So, let us see that the number of particles with unswollen volumes between V1 and V2 is given by NP, that is NP is the total number of particle from V1 to V2, that is the next volume. So, from V1 to V2 it can be represented like this. Now, the total number of particles is usually given by NP is equal to 0 to infinity NV dV. Now, this particular thing is important, and because we have given the enough room for the development of those number of particles, and you know that during the particle size distribution, this particular approach is extremely important. So, if we look that the macroscopic population balance for any CSTR, then it can be represented as like this. So, this is called the particle accumulation. Now, in a different node, we can represent like this, that is Q in, that in an agreement with the reaction engineering concept, that is the entry of particles minus Q out upon V, that is the exit of particles, minus del RV NV upon del V, that is the formation and loss of particles of size v by particle growth. Subsequently, minus n v upon v naught, that is the initial volume, up to, if we carry out up to the infinite time, then it can be represented as k v v dash n v dash d v dash up, that is the loss of particles of size v by coagulation, plus 1 upon 2 v naught, v minus v naught into k v minus v dash n v minus v dash n v dash dv. That is, this is the formation of particles of size v by coagulation of other particles. Now see, we have discussed two concepts over here. One is related to the particle growth, another one is related to coagulation aspect. Now see, coagulation of other particles. Now see, if you recall that when we discussed this particle size distribution, in that category we discussed both the concept that some particles may grow in situ and sometimes they may go in the coagulation with other particles, maybe P1 may be attached with the P2, P3, P4 and so on. Sometimes other particles like catalytic approach, like initiators, etc., they may participate in this type of approach. So we have to look these aspects while developing any kind of mathematical equation. Now in this particular equation, NV and Ni in V are the reactor and inlet number density of polymer particles. Q in is equal to Q out is the volumetric flow rate, that is liter per second inverse. RVV is the volumetric growth rate of a particle of unswollen volume V, and that is again represented as this unit, and K V V dash is the coagulation rate constant for particles of volume V and V dash, and obviously V naught is the volume of particles formed by nucleation. Now this is the initial step where your polymerization process do start. So that particular aspect is extremely important during the consideration. So you cannot overlook the importance of V naught. Now most emulsion polymerizations are generated in the semi-continuous stirred tank reactor, and that is why we adopt this particular approach of implementation in the emulsion polymerization. And sometimes we are always looking for efficient production. Now whenever we look for this efficient production, To achieve these higher production rate, the scale of semi-continuous stir tank reactor is to be increased from to 50 to 60 meter cube for various new units. The production is usually limited by heat removal capacity of the reactor, as these reactions are exothermic in nature. So, in terms of chemical kinetics, the polymerization allows to proceed in better pace then that can be achieved commercially in the industrial practice. So, the use of heat optimization technique, sometimes referred as reflex cooling, these can be implemented, and high pressure monomers like vinyl acetate, they allow the use of such kind of techniques. So, for the example, these high vapor pressure vinyl acetates, they are having the high vapor pressure, and that is why they can be used, these kind of techniques or reflux cooling etc. This can be used for the production of polymers from vinyl acetate. However, in case of monomer exerting low vapor pressures like methyl methacrylate or butyl acrylate, reflux cooling cannot be used as the sufficient pressure cannot be achieved inside the reactor. So, that is why you cannot perform the proper energy efficient system and, if you are adopting this reflux cooling concept. So, to overcome this particular limitation and to improvise the efficiency of heat removal, the reaction medium is usually recirculated through external heat transfer unit, maybe with the heat exchanger or maybe some type of heating fluids etc. So, whatever heat you recovered from these heat exchanger can be used to increase the temperature of feed inside the reactor for the heat optimization. Now, to increase the temperature of inlet water if required for heating, then another approach is that this polymerization reaction can also begin at a lower temperature, and the heat evolved can be finally used to raise the temperature inside the reaction chamber. So, these are the several things which we need to look into during the implementation aspect of these emulsion polymerization. Now, safety is very important consideration in all kind of polymerization reaction and in the practical approach of polymer reaction engineering. Now, the reason is quite obvious that because of the exothermic nature of polymerization reaction, the reactors are prone to undergo thermal runaway, and whenever there is a thermal runaway, there is a chance of material loss, there may be chance of high viscous solution. Sometimes it may create a blast to the reactor. So, in case of emulsion polymerization, the low viscosity of polymeric product, sometimes referred as latex, and involvement of water in the reaction system aid to reduce the chances of thermal runaway. So, sometimes you are having very good liberty to change the temperature profile of the reactor because of the involvement of water. So, sometimes you may add cooling water, sometimes you may add chilled water etc. so that you can avoid the thermal runaway reactions. Now, there are several other factors that can trigger such conditions, like sometimes the failure of cooling system, which can be occurred due to the instrument failure or interruption in power supply. This can cause several bad effect to the reaction and product, like deterioration in the product quality, serious pressure build up inside the reactor, and sometimes if you are using the catalytic approach, then these catalyst may trigger the reaction just like anything. So, that is why this type of minute thing need to be addressed adequately. Industrially, very high pressure changes up to this the range of 600 kilopascal. This has been observed due to the thermal runaway in the emulsion polymerization reaction. Now, there are several pressure handling devices available commercially, like rupture disc, ventilation line to safeguard the reactor from the reaction overpressure, and practical measures such as limiting the amount of free monomer inside the reactor, that can also help to reduce the chance of thermal runaway reaction. So, the key point in this type of safety approaches is that you sensitize, or you must be in a position to look the near misses or near difficulties being carry on within the polymerization reactor. Only then you can adopt all kind of such practical measures to overcome the problem of thermal runaway. Now, another approach which one should look into, that is the quality of polymer. The quality of polymer is a dominant factor which governs the type of reactor and the reaction condition of the polymerization process. The reason is that this is the ultimate thing which you are looking for, and if its quality deteriorates, then definitely your economics or process economics etc. will go on fall. So, that is why this particular approach is invites a very serious attention. Now, the polymers are microstructurally characterized to obtain the information regarding the quality of the product. Now, for the most important and popular microstructural parameter are listed like the copolymer composition. Now, this is one of the most important microstructural parameter, that is to obtain the desired properties inside the polymerization product, as several monomers with a different activity and water solubility are combined together to form a hybrid mixture. So, this is again a triggering approach to get more and more quality polymer product from emulsion polymerization. Now, operating under the limited monomer supply condition, this helps to control the copolymer composition, so that you can improvise the quality of the polymer. The method to achieve such process conditions is usually by feeding the monomer mixture to a lower rate than the rate of polymerization. So, the protocol which you are following in this particular segment is quite critical. Now, owing to the fact that the different monomer partitioning, the composition of polymer formed in the aqueous phase is separate from that of the polymer formed in the polymer particles. The fraction of polymer produced in the aqueous phase is small, but can have a strong effect on its properties. For example, the formation of acrylic acid rich polymer chain that affects the stability of latex, the shear strength of adhesive and the pick strength of coated paper. So, this is a very best example to address this particular issue. The blends of copolymer of a different composition may be obtained by varying the monomer ratio in the feed. Now, as the polymer chains are formed in a very short period of time, the composition of each chain is constant along the chain. So, except for the case of the system in which the intermolecular chain transfer of the polymer occur. So, for such condition, because these conditions are always important, so for such condition each branch has a composition of monomer fed in the moment in which it was formed. So, maybe it may be from the nucleation stage, it may be from the change in the morphological approach frame. So, it all depends on the circumstances. Now, advantage related to the monomer starved process is that the chance of reaction this minimizes as the concentration of monomer inside the reactor is very low. A disadvantage is that sometimes the process is not conducted at the maximum production rate. That means some things you need to get optimized over the period of time. So, the maximum output and good polymer composition can be achieved simultaneously when appropriate online monitoring systems are available. Now let us have a look about the to achieve this particular goal. The total monomer concentration in the reactor is usually chosen to make the rate of heat generation by polymerization equal to the heat transfer rate. So, the monomer ratio is adjusted so that the ratio of polymerization rate equals to the desired copolymer composition, and that is the copolymer composition is referred as F star P1. So, this is equal to Rp1 upon Rp1 plus Rp2. This is equal to F star P1. So, Now, where this the RPJ, sometimes it is referred as RPJ. RPJ is given by Kp1 Jp1 plus Kp2 Jp2 Mj P bar A upon Na Np upon V. This is equation number 2 and this is equation number 1. Now, Pi is the fraction of the active radicals with ultimate unit of type I, that is the monomer. So, you can write the P1 as P1 is equal to K P M1 P upon K P2 P plus K P, and P2 is equal to 1 minus P1. So, that is equation number 3. Now, if we substitute the equation 2 and 3 into equation 1, so the monomer, let me write, substituting equation 2 and 3 to equation 1. So, the monomer ratio needed to obtain the desired copolymer composition P1, that is equal to M2 P upon, which is equal to 1 minus K plus K minus 1 square plus 4 R1 R2 K to the power 0.5 upon 2 K R2, where K is equal to Fp1 upon 1 plus Fp1 star, and R1 and R2, they are the reactivity ratios. So, by this way you can calculate the things based on the knowledge of this. Now, another thing is that we have already talked about in detail about the molecular weight distribution. The molecular weight distribution, as we know, that play a very vital role in deciding the properties of polymer. So, the kinetic length of polymer chain is determined by the competition between the propagation rate and the chain termination rate, because see, the initiation step is always there. So, you need to cut the or you need to adopt the termination protocol at the appropriate level, so that your chain size or and in situ the molecular weight distribution should be well in order. So, any process variable affecting these rates has an influence on the molecular weight distribution. That means the propagation rate and the chain termination rate. So, both of them, they are playing a vital role in deciding the molecular weight distribution. So, these process variables, they are including the initiator type and concentration. If you recall that initiator play a very vital role, it not only initiate the things, but also it facilitate the generation of either free radical and the radical, and these radical may combine together to truncate the chain formation, chain growth. So, by this way the initiator type and concentration, both the things are very much important. Then the number and size of the polymer particles, it is again very crucial with respect to the approach that larger the size, larger the number, then larger the molecular weight, then larger the molecular weight distribution, and therefore the property may affect adversely or sometimes maybe favorably. So, The another aspect is the temperature and monomer concentration. It is quite obvious. We have already discussed that this play a very vital role in deciding the fate of molecular weight distribution. So, these process variables strongly affect the other kinetic aspect, that is the polymerization rate. So, the molecular weight distribution is better controlled by means of both chain transfer agents CTA and the multifunctional monomers, and both the concept we have discussed in the previous lectures. Now, in the presence of chain transfer agent, the chain transfer agent is the main chain termination event, and instantaneous molecular weight distribution has a number average chain length given by this particular mathematical equation. Now, here the polydispersity index, this is PDI is required as 2. So, therefore, the instantaneous molecular weight distribution can be controlled by adjusting the monomer upon chain transfer agent ratio. Now, the non-linear polymers, they are frequently characterized by their solubility in a given solvent. So, the insoluble part which correspond to high molecular weight, heavily branched polymer, and the polymer network usually called gel. Now, in polymerization of monofunctional monomer forming gel by intermolecular chain transfer to polymer formed by termination, maybe by the combination. So, all kind of permutation combination theories are applied over here for the formation of these gels. Sometimes multifunctional monomers, they are used to create the polymer network. Now, relatively this is the modest approach, and modest amount of bifunctional monomer, sometimes maybe 0.5 mole %, they are enough to obtain a very high gel fraction. It may go up to say 90% sometimes. However, the sole molecular weight decreases severely. So, an independent control of molecular weight distribution and the gel content, this can be achieved by balancing the concentration of chain transfer agent and the multifunctional monomer in the formulation. So, you may say that the concentration of chain transfer agent and the concentration of multifunctional monomer, these can be optimized to get the adequate result as per the desired of molecular weight distribution concept. Now, sometimes the post treatment of latexes with initiator system, they producing very high reactive tertiary butyl radicals in usually a way of modifying the molecular weight distribution. So, usually it lowers the molecular weight of vinyl acetate rich polymers by hydrogen abstraction, usually followed by beta cis and led to the gel formation in acrylic polymer by hydrogen abstraction, usually followed by termination of combination. Now, this represent a possible way, or you may term that this is an example to extend the range of properties achievable by given base emulsion polymers. Now, this particular approach is extremely important while you consider the economics of these emulsion polymerization process. Now, let us have a look about the particle size distribution, because again it is a key factor in deciding the polymer properties. Now, the particle size distribution strongly affects the rheology, because we always talk about the viscosity, we always talk about the processability of those polymers developed in due course of any polymerization process. So, particle size distribution, it plays a vital role in deciding the fate of rheology. Now, usually this rheology in turns influences the heat removal rate, mixing, mass transfer and stability of various kind of polymer being generated. This particle size distribution affects film formation and some application properties, and usually it is the result of competition between the nucleation, particle growth and coagulation. So, you see that all these three things are the participating parameters in the particle size distribution: nucleation, particle growth, because the particle may grow up to any extent, then coagulation, because 2 particles or 3 particles, 4 particles may combine with in situ or some other particles to form a coagulant, then these things affect the rheological approach of those polymers being developed in the emulsion polymerization. Now, the particle growth broadens the particle size distribution because of higher number of radicals in the larger particle. Now, particle nucleation usually depends on the availability of emulsifier. If any emulsifier is available, then the nucleation is affected by the availability of these emulsifier. Then radical generation rate, how much radical being generated, maybe in a positive sense or maybe in the negative sense. Then the water solubility concept of monomer. Then the number of particles, those who are already present within the system. So, these parameters are playing a very vital role in deciding the fate of particle size distribution. Now, easy way of nucleating the new particle is to add enough emulsifier to form micelles. So, that if you recall the figure, that micelle may grow up in size. So, the larger the surface area of polymer particle, the more emulsifier is needed to form the micelles. So, sometimes it may create the depletion of emulsifier within the mass in question. Now, the amount of particles nucleated through the heterogeneous nucleation, they generally rises through increase in the concentration of the initiator. Now, this is not usually a good practical process for the control of particle size distribution, because it usually affects the polymerization rate, molecular weight distribution, and the polymer architecture. So, this thing should be looked into while considering this particular approach. Now, homogeneous nucleation, which we discussed earlier, often yields secondary nucleation in system in which there are no micelles. Now, the homogeneous nucleation rate sometimes increases with the concentration of monomer in the aqueous phase and the initiator concentration. Now, it decreases with the increase in the number of particles. So, in other words, we may say that secondary nucleation sometimes is very difficult to avoid in the larger particle size containing water soluble monomers, sometimes for example like acrylic acid, etc. So, irrespective of nucleation mechanism, the newly formed particles sometimes undergo a substantial increase in size, maybe because of the polymerization. So, therefore, they need additional emulsifiers. So, this type of thing mathematically should be performed, mathematically should be calculated, that how much quantity of additional emulsifier is required to carry out the polymerization process to complete. Now, fast diffusing anionic emulsifier, they are much more efficient at stabilizing the new particle than the slow diffusing non-ionic emulsifier. So, the quality of emulsifier is also play a vital role in deciding the fate of particle size distribution. So, the greater number of polymer particles, they may be generated using the ionic surfactant, because they alter the surface energy of the media. Now, coagulation usually is a second order process. Therefore, its rate usually increases with the concentration of polymer particles, maybe by increasing the solid content and decreasing the particle size. So, particle stability is the key aspect in controlling the coagulation. Now, the first condition for stability is that they must have a sufficient coverage of the polymer particles. So, that there is a minimum arena requirement, and they must cover to form those arena, so that they can form the coagulation. The efficiency of the surfactant may be severely affected by the process condition. Therefore, the ionic strength sometimes reduces the efficiency of ionic surfactant. Now, deionized water is commonly used in the emulsion polymerization, and excess of inorganic initiator may cause coagulation. So, that is why you see that deionized water, because this minimizes the presence of any kind of ions through the water media. The strong agitation may cause the shear induced coagulation. So, narrow particle size distributions usually are obtained when all the particles are formed during the polymerization of the initial charge, and neither secondary nucleation nor coagulation they occur during the semi-continuous operation. Sometimes high solid content may be greater than 55%. Latexes are advantageous because they maximize the reactor production, minimize the transportation cost, and sometimes give more flexibility in product formulation. So, sometimes if you wish to transport the things from one place to another place, and if they are having the high density, then obviously they will require less volume for the transportation, and the transportation cost may be a bit minimized. So, the maximum solid content is usually limited by the viscosity of the latex. Bimodal particle size distribution with the small particles sometimes accounting for say 28% of the polymer, they minimizes the latex viscosity. And bimodal particle size distribution, usually they are produced by creating the second crop of polymer particles by adding a shot of emulsifier. So, alternatively, another method is given to produce the bimodal particle size distributions are the growth of bimodal sheets and controlled partial coagulation of monomodal latex. So, in all cases, the formation of undesired particle by homogeneous nucleation should be prevented. So, in this particular chapter, we discussed about the concept of particle size distribution and applied to the emulsion polymerization. Then we discussed the various parameters essential for the implementation of emulsion polymerization. For ease of your reading, we have enlisted a couple of references for your further studies. We will continue this implementation aspect in the next lecture. Thank you very much.